Large language models, or LLMs, have made impressive strides in generating text and handling complex reasoning tasks. However, when these models are deployed in real-world applications, they often encounter significant challenges. Sometimes they hallucinate, meaning they generate responses that sound plausible but are actually incorrect. Other times, they provide outdated information. Retrieval-Augmented Generation, or RAG, was introduced to address these issues by grounding LLM responses in external documents. While this approach reduces hallucinations, it's not a perfect solution. Traditional RAG systems process external information as raw, unstructured text, which can be messy and confusing. This makes it difficult for the system to answer complex questions that require multi-step reasoning. So, why does RAG struggle, and what can we do about it? Let's dive in. Traditional RAG connects LLMs to external information to help reduce hallucinations and keep responses up to date. However, even with this improvement, RAG still faces limitations. The main issue is that it processes documents as unstructured text passages. This unstructured text often includes irrelevant details that can mislead the model and result in incorrect answers. When faced with complex questions that require organized, domain-specific knowledge or multi-step reasoning, traditional RAG systems often fall short. The lack of structure in the retrieved information makes it hard for the model to connect the dots and provide accurate, comprehensive answers. To overcome these limitations, structuring the retrieved data is essential. By transforming unstructured text into organized, actionable knowledge, we can address the key weaknesses of traditional RAG. Structured data allows the model to see clear connections between facts, making it easier to handle complex queries that require deeper reasoning. For example, using knowledge graphs to guide the model ensures that responses are more accurate and grounded in verifiable information. Structuring not only improves the quality of the answers, but also reduces the risk of hallucinations, making the system more reliable. This is where the retrieval and structuring, or RAS, paradigm comes in. RAS extends the traditional RAG approach by adding a crucial step, knowledge structuring. Instead of just retrieving raw text, RAS organizes the information using techniques like taxonomies and knowledge graphs. This structured approach allows the model to reason more effectively and verify its answers. The RAS framework unifies three key components: information retrieval, structured knowledge representation, and large language models. By combining these elements, RAS creates a more robust system for handling complex, knowledge-intensive tasks. Let's break down how RAS works in practice. First, the LLM retrieves all relevant documents related to the query. Next, instead of pulling in raw, unstructured text, the system organizes this information into a structured format, like a knowledge graph or taxonomy. This step eliminates confusion and isolates the key facts and relationships. Finally, the LLM uses this organized knowledge to construct a factual, accurate, and easy-to-verify answer. By teaching the model not only how to find information, but also how to organize and reason with it, RAS significantly improves the quality of responses. One of the foundational principles of RAS is structure-enhanced retrieval. This means using structuring techniques to help the retrieval system find exactly what the LLM needs, especially for complex or domain-specific questions. There are several ways to enhance retrieval. Taxonomy-based approaches use topic taxonomies specific to the domain, guiding the search in a more meaningful way. Knowledge graph-based approaches allow the model to move through relationships and connections, not just keywords, and iterative cycles combine these methods, refining the search and structuring process with each step. Once the knowledge is structured, the next challenge is using this structure to enhance the LLM's responses. Structure-enhanced generation grounds the model's answers in explicit knowledge structures, which greatly reduces hallucinations and improves factual consistency. Techniques like think-on-graph, 2G, and graph of thought, GoT, enable the model to reason directly with knowledge graphs, building explicit reasoning chains step by step. Other methods, like GraphRag, condense complex structured knowledge into text summaries, helping the model handle queries that require a global understanding of the information. The first step in adding structure is creating core representations like taxonomies and entities. A taxonomy is a tree-like structure that organizes concepts from broad categories at the top to more specific ones below. In text mining, Taxonomies help structure labels and organize information. Construction starts with a basic seed, which is then expanded and refined. Tools like HiExpan and Corel automate this process, growing the taxonomy step by step and ensuring that each group of child nodes remains coherent and relevant. This foundational structure is crucial for organizing domain knowledge. After building the basic taxonomy, the next step is enrichment. This involves associating each node with descriptive text or keywords, making the structure more informative and discriminative. Techniques like Taxogen and NetTaxo automate this process by clustering related terms and refining the clusters using local corpora and network structure information. The result is a richer, more accurate hierarchy of topics that makes it easier to discover main themes and their subtopics. This step ensures that the structured knowledge is both comprehensive and easy to navigate. Information extraction is a key step in building structured knowledge. This process focuses on identifying real-world entities and the relationships between them, which are essential for constructing knowledge graphs. Techniques like named entity recognition, NER, and fine-grained entity typing, FET, help extract and categorize entities, while relation extraction identifies how these entities are connected. By mining entities and their relationships from text, we create the building blocks for a robust knowledge graph that can support complex reasoning tasks. Once entities and relationships are extracted, the next step is constructing the knowledge graph. This involves representing real-world entities as nodes and their relationships as edges. There are several approaches to building knowledge graphs, including pipelined methods like open information extraction, OpenIE, end-to-end models like Rebel, and LLM-based methods such as Knowledge Graph GPT. These frameworks automate the process of converting raw text into structured graphs, making it easier for the model to reason and generate accurate answers. Implementing structured knowledge in RAG systems is now more accessible thanks to tools like the KGGen package. This Python library uses LLMs to build high-quality knowledge graphs directly from plain text. It groups related entities together, reducing sparsity and making the graphs more useful. The package supports processing large texts in chunks, clustering similar entities, and aggregating multiple graphs. These features make it easier for developers to add structure to their RAG systems and improve their performance on complex queries. Advanced RAS systems use a dynamic, iterative cycle to build and refine structured knowledge tailored to each query. The process starts with action planning, where the system assesses the question and generates targeted subqueries if needed. Next, theme-scoped retrieval narrows down the search to the most relevant documents. Then, dynamic knowledge structuring organizes the retrieved information into a growing knowledge graph. Finally, the answer is generated using this structured knowledge, ensuring accuracy and coherence even for complex, multi-step questions. Despite its advantages, RAS faces several technical challenges. Retrieval efficiency is a major concern, as larger models and databases increase the strain on retrieval systems and can lead to higher latency. Maintaining knowledge quality is also difficult, as automated tools can introduce errors or inconsistencies. Integration complexity arises when trying to reconcile information from multiple sources and keep everything up to date. Balancing performance with richer reasoning capabilities remains an ongoing challenge for researchers and developers. Looking ahead, the RAS approach is evolving to handle even more complex data and user needs. Future research is focusing on multimodal knowledge integration, allowing systems to reason across text, images, video, and audio. Cross-lingual systems will enable knowledge sharing across languages. Interactive and self-refining systems will support natural query refinement and self-correction. Human-AI collaboration will combine machine scale with expert judgment, and personalized knowledge delivery will make retrieval more relevant to individual users. These advancements will help RAS systems become even more reliable and adaptable. In summary, the retrieval and structuring (RAS) paradigm represents a major step forward in making LLMs more reliable and knowledge-driven. By transforming unstructured data into structured, verifiable knowledge, RAS addresses the core weaknesses of traditional RAG systems. While challenges remain in terms of speed, quality, and integration, ongoing research and new tools are paving the way for smarter, more adaptable AI applications. As RAS continues to evolve, it promises to deliver more accurate, coherent, and trustworthy answers even to the most complex questions.